Something is amiss in our understanding of the universe. Cosmology is apparently setting out toward a showdown on one of its most essential questions. How fast is the universe expanding? For over a decade, two types of measurements have been in conflict. Observations of the current universe often find the rate of expansion, called the Hubble constant, to be around 9% faster than predictions based on early universe data. Experts believe that the James Webb Space Telescope, the most advanced telescope ever built, would help resolve the question definitively. However, consensus has so far failed to emerge. Instead, the Superior Observatory has intensified the discrepancy with incredibly precise, novel observations that threaten to overturn the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a subject of debate. A surprising and captivating possibility that there's something we don't understand about the universe. Join us as we delve deep into how new ultra-deep images from James Webb have recently confirmed that there is indeed something truly amiss with how we interpret the universe. Our universe began with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting moment. Then the young universe was formed, a growing, swirling plasma full of matter and antimatter particles that popped into reality only to annihilate each other upon contact. Left to their own devices, the matter and antimatter within this plasma would have consumed each other completely. However, scientists believe some mysterious imbalance allowed more matter than antimatter to be created, saving the universe from a quick collapse. Gravity compressed the plasma pockets, crushing and heating the matter so that sound waves, traveling at half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high-energy density of the early universe's dense content expanded spacetime, pulling a portion of this plasma safely from the fray. As the universe expanded like a balloon, the standard story goes. Normal matter, which interacts with light, coalesced around clusters of invisible dark matter to form the first galaxies, connected by a massive cosmic web. Initially, as the universe's content spread out, its energy density, and thus its expansion rate, decreased. However, about 5 billion years ago, galaxies began to recede from each other at an ever-increasing rate. The reason was another invisible and perplexing substance known as dark energy. The simplest and most famous explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe expanded, its general matter density dropped, while the dark energy density remained the same, gradually making dark energy the dominant contributor to its overall growth. Included in the energy densities of normal matter, dark energy, and light are the upper speed limits of the universe's expansion. They are also key ingredients in the lambda cold dark matter, lambda CDM, model of cosmology, which governs the expansion of the universe and predicts its eventual end when matter is so spread out that it experiences a thermal death, known as the Big Freeze. Many of the model's predictions have proven remarkably accurate. But here's where the problems start. Despite extensive searching, cosmologists still do not know what dark matter or dark energy actually are. As Ofer Lahov, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "The vast majority agree that the universe's current makeup is 5% normal matter, 25.5% cold dark matter, and 70% dark energy. The embarrassing truth is we don't know the last two." However, an even greater challenge to the lambda CDM model has emerged. Depending on which method astrophysicists use, the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Methods that account for the early universe show it expanding much faster than the lambda CDM model predicts. These methods have been tested and verified by numerous observations. For example, Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb estimates, said, "The only reason I can understand for them to differ is that the model we have between them is perhaps missing something. Measuring the universe's expansion takes more than a radar gun. The main method to measure this expansion examines the so-called cosmic microwave background, CMB, a remnant of the universe's first light created just 400,000 years after the Big Bang. This imprint should be visible across the whole sky, and it was used to determine the Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this baby picture of the universe, the cosmos is predominantly uniform. However, hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations caused it to cluster together. As the universe expanded outward, this soap bubble structure grew into the vast cosmic web, a network of filaments along whose intersections galaxies would form. By studying these waves with the bored satellite, cosmologists assembled the measures of typical matter, dark matter, and values for the cosmological constant, or dark energy. This is connected to the Standard Model, which yielded a Hubble constant of around 67 kilometers each second per megaparsec. A megaparsec is 3.26 million light-years. Let's pause on this number briefly. If a galaxy is 1 megaparsec away from us, it means it will recede from us, and we from it, at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to increase dramatically from there. If a galaxy is more than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheids, dying stars with helium gas outer layers that expand and contract as they absorb and emit radiation, causing them to periodically glow like distant signal lights. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid was, the slower it would pulse, allowing cosmologists to gauge a star's absolute brightness and thus its distance. This was a landmark discovery that transformed Cepheids into abundant standard candles for measuring the universe's large-scale structure. By combining observations of pulsating Cepheids, cosmologists can build distance ladders, each step taking them further back into the past. To build a distance ladder, astronomers start by selecting nearby Cepheids and cross-checking their distances based on pulsating light with what's found by geometry. The subsequent steps are added using Cepheid readings alone. Then, cosmologists look at the distances of stars and supernovae on each rung and observe how much their light has been redshifted, stretched into longer, redder wavelengths as the universe expands. This provides an accurate measurement of the Hubble constant. In 2019, this method was used by Rees and his colleagues, who trained the Hubble Space Telescope on one of the Milky Way's nearest neighbors. According to the standard picture of cosmology, the universe began as an inflationary vacuum. It had a high energy density and intense gravity, causing it to expand. The more energy there was, the greater the repulsion and the faster it expanded. In line with quantum principles, this vacuum was random in localized areas, where it decayed into the normal vacuum, creating matter and heating it to a blisteringly high temperature, resulting in Big Bangs. Our universe is just one such Big Bang bubble in the ever-expanding inflationary vacuum. Incredibly, this entire process could have started with a lump of inflationary vacuum with a mass comparable to a packet of sugar. Conveniently, the laws of physics, specifically quantum physics, allow such matter to spring into reality from nothing. Of course, the next obvious question is, where did the laws of physics come from? In 1918, German mathematician Emmy Noether shed light on this. She observed that conservation laws are fundamental consequences of deep symmetries in existence, properties that remain constant even when our perspective changes. A remarkable property of such symmetries is that they are also symmetries of the void, of a completely empty universe. So, perhaps the transition from nothing to something wasn't such a big deal. Maybe it was merely a transition from nothing to an undifferentiated something. But why did this transition occur? American physicist Victor Stenger highlighted that as temperature decreases, water transforms into organized ice because ice is more stable. He speculated that the universe went from nothing to an undifferentiated something because an organized nothing is more stable. Why is there a massive black hole at the center of nearly every galaxy? There are around 2 trillion galaxies in our universe, and as far as we know, almost every one contains a central supermassive black hole. They range in size from behemoths weighing nearly 50 billion times the mass of the Sun to the 4.3 million solar mass giant known as Sagittarius A** at the center of our Milky Way. Yet, how they got there is one of the great unresolved problems of cosmology. We know that a stellar black hole forms in a supernova, where a star's core collapses, But no one knows how a supermassive black hole forms over the course of most cosmic history. The centers of galaxies have been places where large amounts of matter accumulate in a small volume. It could be that supermassive black holes form in dense star clusters made up of stellar black holes, which repeatedly merge with one another. Indirect evidence for this comes from a merger between two black holes detected by gravitational waves, where one black hole was too massive to be a remnant of a stellar explosion, and thus may have originated in an earlier merger. Another way to form a supermassive black hole is through the direct collapse of a massive gas cloud. It's possible that supermassive black holes form from a combination of gas cloud collapse and black hole mergers. It's also possible that supermassive black holes formed in the Big Bang itself. This would answer the cosmic chicken and egg question. Which came first, galaxies or supermassive black holes? Instead of galaxies forming first and then spawning these giants, it could be that supermassive black holes formed first and provided the seeds around which galaxies of stars formed. Despite their masses, even the largest supermassive black holes are not bigger than the nearby planetary system. But they project their power across billions of light-years through oppositely directed, extremely fast jets of matter. Where these jets are fast in the inner regions of a galaxy, they drive gas away and inhibit star formation. Where they slow down in the outer regions, they compress gas and trigger star formation. In fact, powerful jets from the largest black holes seem to regulate most of the stars that form, with a preference for smaller, cooler stars like our Sun. So who knows? It might be that we can thank Sagittarius A** for our Sun, without which we probably wouldn't be here now. Dark matter. Dark matter emits no light or too little light for us to detect. We know it exists because we can see the effects of its gravity on visible stars and galaxies. For example, the Milky Way could never have attracted enough matter to form stars in the 13.8 billion years since the Big Bang without a lot of unseen matter whose additional gravity sped things up. The European Space Agency's Planck satellite found that dark matter accounts for 26.8% of the universe's mass energy, compared to the 4.5% of ordinary baryonic matter. It thus outweighs visible stars and galaxies by a factor of about 6. For years, the favored candidates for dark matter particles have been weakly interacting massive particles, or WIMPs. However, although these particles fit the bill, they have failed to show up in experiments at the Large Hadron Collider near Geneva, Switzerland. A candidate gaining favor is the ultralight axion, a theoretical subatomic particle. Another idea is that dark matter remains as primordial black holes left over from the Big Bang. Mysteriously, no Earth-based experiment has found any evidence of dark matter, despite decades of searching. Perhaps our theory of matter needs adjustment, or our theory of gravity. Or maybe dark matter isn't a fluid made of a single particle but something more complex, like the ordinary matter we see around us. Perhaps the universe is full of dark stars, dark planets, and even dark